Okay, here we are talking about polyatomic ions. So they're going to be a lot like the other ions we've seen so far, which would just be the binary ions. But this are going to be a little bit different in that it's not just going to be two elements anymore when we decide on what a compound is going to have for its formula or what its name is going to be. So we're going to look at this special type of ion called a polyatomic ion. And what they are consisting of is there are several atoms that act together as a group, but collectively they have a single charge on them. So for example, you can see nitrate and ammonium at the bottom here, and you can see that this is the group that makes up nitrate, this is the group that makes up ammonium, and collectively as a whole they have a charge. Now, what's interesting about all of these things is that they're actually types of molecules. You'll notice that they have these lines in between them. We didn't do any lines in our ionic compounds. We just talked about them staying together because they had opposite charges, so pluses and minuses and so on. But you notice that there are these lines here. And what these lines represent is a covalent bond between atoms. So it's a different type of bond than an ionic bond. Those orange things are referring to covalent bonds. Now, we haven't got to that yet, but you already know a little bit about them. That's about the sharing of electrons, and we'll cover that very shortly after we finish our acids. So those are covalent bonds, okay? And those are from sharing electrons. So you'll see things like this, where there's a single line that represents single bond, and these double lines represent double bonds and whatnot. Okay. Now, because there is these bonds in here, technically this thing here, unlike our regular ions, this is actually a molecule. Oh, a molecule. And it's not just a single entity. So you notice that all these things are forming a molecule because they're sharing those bonds, but overall they have a collective charge of a minus. Okay, so you'll see things later on in our table like nitrate and ammonium and so on. You can see ammonium has those covalent bonds in it as well between the different elements that make up this collective group and whatnot. Okay. Now we treat the whole molecule as a charged thing, this whole group. So what we do is we simplify it. We don't usually draw the full structure. We just simplify this structure as just NO3. So N and then 3 O's, O3, and then we represent the number of the charge on it by a 1 minus. Or you can just say minus, it's fine. It's just as good to say NO3 and then minus. You just have to remember there's a 1 there. Same thing over here. You're going to reduce this structure down to just simply N and then 4 H's, NH4, and then you can rewrite this if you like as well, NH4, and then you can just say plus, whichever. It doesn't really make any difference. Okay. The key thing to remember is that they're a group of atoms that are bonded, a molecule, that they share over the entire ion or the molecule this charge. So we won't talk about one particular part of it. Some of these are going to have resonance, which means that the charge moves throughout the molecule, is not just located in one particular space. So we draw it as collectively just being a negative charge. Like these two, for example, I think the charge kind of moves around, but that's something you'll do in grade 12. Okay. All right, now the polyatomic ions, the rules for writing the atomic atom or the polyatomic atoms are essentially for formula writing and naming is the same as the binary ionic. And we talked briefly about this, about the binaries. Everything you've done so far is considered a binary ionic compound. And what makes it binary is that each of the compounds you've made so far only have 2 elements. So an ionic compound that only has 2 elements in it. So for instance, NaCl, NaCl, there's 1 element, there's 2 elements. That's a binary compound. Now polyatomics are not going to be binary because if you look at ammonium up here, there's already 2 different types of elements that make up its composition, and it's going to have to be attached to a negative ion to form the ionic compound. So we know that there's going to be at least a 3rd element in there. So it would no longer just be 2, so no longer binary. Each polyatomic is treated as a single unit. So we'll get in the habit of not thinking necessarily like this, but just as these groups. This is always a group. This is always a group, and so on. And you'll get more familiar with that as we move forward and you get more experience in those things. Okay? So if you look at the table below, this is just a table of some common polyatomics. So keep in mind, these are common ones. They're not the only ones. Okay? So the ones that are highlighted, so ammonium, carbonate, sulfate, hydroxide, chlorate, nitrate, and phosphate, they're the ones that you're going to have to kind of memorize. So the parts that you're going to have to memorize are clearly the name. You're going to have to memorize the formula. And you're also going to have to memorize the charge. Okay, so there's 3 things about those 7 you'll have to know. Now, of course, the more you use these, the more familiar you'll get, and you won't be just a straight memorization. You'll just remember because of constant use and so on. Now, some other ones are listed on here as well. Acetate, chromate, cyanate, cyanide, and then permanganate. These are other common ones, but they're not ones that are required necessarily, but they might pop up in a couple of our questions, so they're in the table here. In addition, if you see one of the questions that are assigned to you and you notice they're not in the table, just Google it, because there's a lot of different polyatomics. This is just a sampling of the common ones. Okay. Now you'll notice that acetate has 2 different forms. This would technically be the better form in our idea of just kind of taking the symbols from the group and then putting them together. The reason they draw it like this is because there is a specific way that these, in molecules, there's specific ways that the elements arrange themselves or are bonded. And this structure implies that this carbon has 3 hydrogens around it, and this carbon is attached to one of the carbons, we'll talk about that later, but also to these 2 oxygens. So they're more closely associated with this, and these are most closely associated with this, whereas this just shows you the composition. But you can use either of them. It doesn't really make any difference. This just might be easier because this is the groupings of everything. Okay. All right. So this is the basic representation of the polyatomics. So the ones that have kind of these are a baseline, kind of considering that there are going to be alterations in some of their formula. So these are the ones that are given here are just the basic polyatomic unit. Okay. And the ones that have variance in their formula is the ones that have oxygen. So they can vary in their numbers of oxygens that they have. Okay. So the way to remember this, the ones that do have variation in those oxygens end off with the ending ATE. Okay. The ones with ATE on the end, so the 8s, they all vary in O2 amounts or their oxygen amounts. Which means that if you looked at carbonate, so the 8 version of that is CO3, but there could also be a CO2 or maybe a CO4 and so on. They can vary in there, but this is the one that represents the 8. Okay, so that's the one that we'll remember as carbonate, and then there's the one we'll remember for sulfate, hydroxide, chlorate, nitrate, and phosphate. Now, because there's no 8 on the end of hydroxide, it's not hydroxoate or hydroxate, that means that there's no variation in the oxygens. Just like ammonium, it's not ammoniate, so there's no variation in oxygens. In fact, there's no oxygens there, so that's a dead giveaway for that. But the ones that have 8 in them, they're the ones that can vary in their numbers of oxygens. So unless there's an 8 on the end, they're always in that particular structure. Okay, so let's go into how this variation in oxygen can affect, I guess, how we name some of these ions and think about them and use them and so forth. Okay, so table 2 down here gives you the system for determining polyatomic ions name and also the formula as well, if you have the name and so forth. When the number of oxygen atoms is less than the formula of the ones that we saw in table 2. So if the name of your polyatomic doesn't have 8 on the end, then we're going to consider how many oxygens have changed. Or if you see a structure that has less than the carbon 8, that let's say that's the beginning, that has more or less than 3, we're going to have to see how that name is going to change and so on. Okay. Now the way this table works is this is telling you how many oxygen atoms I have. And we said that the normal amount would also be from table 1, that's the basic unit that we recognize as one of these polyatomics of that particular type. So in this way, the table is looking at chlorate. So the normal or basic is the 8 version of that. Okay? That was from table 1. So if I remember chlorate, it's ClO3 and it has a 1 minus charge or minus charge. However, I can see that if I get one more chlorate, it's going to be COLO4, and then we change the name to represent that change. So it's still the same version, but we're going to make an alteration to the name to let us people know, or we're going to look at the formula and then tell people that it's going to have a different name. And we add this per section and we use the same ending. Okay? And we'll notice here that there is one extra, right? So that's one more down there than the basic version. Okay, so more O. All right, so we got the more O's in there. We can always use this table as well. So if we notice that there's one less, or someone tells us that the ending is ITE as opposed to 8, then that's going to let us know that there's one less oxygen. So that becomes ite on the end. Okay. So one less O. And you'll notice that this kind of system continues. We use the same change as one less to get to 2s. So it's still ite on the end, but it also has a prefix of hypo. So then we change our name to be hypoite, and whatever the base unit was for that particular one. And the one before it would be chlorite, hypochlorite, for one that has 2 less oxygens. So there's now nothing down there. Okay. Now the one thing I want to mention is the oxygen contents have changed, but the charge does not change on the polyatomic. So for all intents and purposes, even though the formula has changed, the way that the ion behaves is exactly the same. There's no change to the way that it performs. It's still just a 1 minus, a 1 minus, a 1 minus, a 1 minus. Only the structure and the name changes. Okay. So if we had to look at something like nitrate, let's put that into practice here. So nitrate is our basic unit. So then we're going to write all the variations that we could potentially have for this. So if I had NO4, 1 minus, this would be per nitrate, because I have one more, I add per, and then 8, per, and then 8, and then whatever this is nitrogen, so per nitrate. All right, so they can also have NO2, which would be 1 less, so that's my ite. So this would be nitrate. And then I'm going to go 2 less with NO, no. And then this would be 2 less, so then I would use the hypoite. So this would be hyponitrite. So pretty easy once you get used to that process of knowing what the base is. If do I have more, do I have less, how many less, and so on. Same thing here. This is sulfate. So if I have SO5 2 minus, this would be per sulfate. Okay. If I have SO3 2 minus, that's going to be sulfite. All right, and then if I have 2 less, so SO2, then I have hyposulfite. Pretty straightforward in that sense. And you'll get more familiar with this as you get more familiar with the basic 8 versions of these, and then just knowing the system of going above or below the normal amount of oxygens. All right. So we're going to get into the practice of writing chemical formulas and also writing correct names based on our system. So they work towards one another. Once you know the name correctly, you can then write the correct formula. If you have the formula, then you can write the correct name. So the first thing we're going to do for chemical formulas, we're going to identify the positive ion and then the negative ion. Notice that I don't say metal here because some of our polyatomics have a positive charge, as other things will be as you expand your understanding of chemistry. Not only metals will have positive ions. So if we just go back to our previous sheet, we'll notice that this polyatomic here, ammonium, it has a positive charge, and it's not a metal. So we can't just say metal and then non-metal. What we're going to get in the habit of saying now is which one of these things in my compound is a positive ion and which one of them is a negative ion. Okay? Then we're going to find the chemical symbols for those ions. We're going to draw them down or write them down. We're going to determine the charges, and then we're going to do our charge balance like we did before, although we don't need to do a full equation for it. We won't do equations for polyatomics. And then we're going to write the formulas. Okay, so we're going to use aluminum phosphite. So here's aluminum phosphite. Okay. So what we're going to do with that is we're going to write down the charges of the ions and their ions first. So aluminum is 3 plus. Phosphite, so I know it's going to be PO. Phosphite tells me that it's 1 less than the normal PO4, so it's going to be PO3. And then it still has the same charge of 3 minus. Okay. Now, next thing I want to do for formula is I want to see if these charges are balanced and that they would cancel each other out, and they do. So this would just be AlPO3, and that's it. Same thing for calcium hypochlorite. We're going to write down the charges of the two ions here. So calcium is Ca2 plus, and chlorite is ClO. Now normally it's ClO3. This is hypo, so it's 2 less. So it's just going to be ClO or Clo, and then it's a 1 minus charge. Now you will notice that this charge is twice as big as that charge. So in order for my clos or hypochlorites to balance off this, I'm going to need more of these. So I'll need a second one in there. So what I want to do is I'm going to make 2 of these. Okay, and then therefore I'm going to write my formula as Ca. And now there's 2 of them, but I only need to represent them as a group. So I'm going to put that group in a bracket, and then the 2 goes here. Okay. Now what I want to mention here is that if you have more than one of a polyatomic, you write it in a bracket, and then the subscript of how many you need. If you don't have more than one, you don't need a bracket because there's only one of them there. Now, the reason that this is important to have it as a group is because instead of having this in a bracket, what if I use this number and just simply attached it to this, and I wrote CaClO2? This would be incorrect because this is supposed to tell me that I need 2 whole groups of this, like that. But if I do it like this means I've only kind of added the oxygen, but I haven't made a second chlorine and so on, and this would be incorrect. Okay, so if the polyatomic is there's going to be more than one of them in the formula, 2, 3, 4, whatever number higher than 1, put them in a bracket. If there's only one, you don't need a bracket. Okay, one last thing we're going to do before we end this off is we're also going to talk about the influence that hydrogen ions have on some of these polyatomics. So some of the negative ones, so the 8s for the most part, the ones that vary in oxygens, they have a certain capacity to capture hydrogen ions. And when I use the word capture, really what it means is form a covalent bond. With hydrogen. And when it does that, it kind of eliminates some of the charge. In fact, it eliminates one of the charges in a negative ion, and we'll just kind of show what that looks like. Okay. Now, each one does neutralize that minus charge. Okay. Now, the reason we say that each one, because some of them can grab more than one, and it's going to influence the charge. Now, remember, the oxygens that are added to the formula do not change charge. But when hydrogens are added to the formula, they do change charge. Okay. So we're going to use carbonate as an example here. So carbonate is normally CO3 2 minus, but there are forms of carbonate where it has captured or formed a covalent bond with a hydrogen and becomes this structure over here. Okay. Now the only difference between these 2 structures is the H. So no H, H. And then what each H does is it reduces the charge, the negative charge, by 1. So it was -2, now it's -1. That is a difference of 1. Okay? And then we're going to look at examples where there could be 2 and so on. Now, if you did add another hydrogen, let's say we captured another, then you would end up with H2CO3, but I would have to reduce this by 1, which would make it 0, so there'd be no charge anymore. So this is not an ion. So it is no longer a polyatomic. What it actually is a fully charged or a completely neutral molecule. Okay, so just keep that in mind. Is that in order to be still a polyatomic ion, you need a charge left over. Grabbing two H's bicarbonate would not have a charge left, so therefore this is no longer an ion. Okay, so CO3 can really only capture one to still remain a polyatomic, although it could capture two and become a non-polyatomic, just become a regular molecule. Okay. All right, so the naming system for this is slightly different. Okay, if you have captured one hydrogen ion, you can change the name to be hydrogen or bi. So for instance, if I had, let's say, carbonate, like we did at the top here, if I captured one hydrogen, it would still be carbonate, but now we call it hydrogen carbonate, or you could also call it bicarbonate. Okay. And remember that when you have your CO3, it's normally 2 minus, but because you captured 1H, it reduces the charge by 1. So it goes from 2 minus to 1 minus. Okay. Also, this is another example. You could have hydrogen sulfate or bisulfate. And again, the charge is reduced. Normally it's SO4 2 minus, but it's going to get changed because of the hydrogen to a 1 minus. Okay. I think phosphate is the only one that can really do this, capturing two H's. So you can change the name to dihydrogen. So it would be dihydrogen phosphate. And notice that PO4 is normally 3 minus, but because I've captured two of these, this goes down by 2. Okay. There is no bi version of this, so they just use the one dihydrogen phosphate. Okay. All right. So we're going to name these together, or we'll just do it as an example, I guess. So we're going to write our positive ion, and then we're going to establish our negative ion. So our positive ion here is the metal sodium, Na. Oh, I guess we're just naming it, so I don't really have to do that. Okay, so we're going to name this up. So we're going to first do the metal here. So this is sodium. And then our polyatomic here, in this case, is this whole group here. And this is one that carbonate that has captured an H. So here's capturing an H. So it's going to be this version of carbonate. So this is going to be sodium bicarbonate, or it's going to be sodium hydrogen carbonate. Okay. This one over here is going to be lithium. And this is a phosphate that has captured two H's. And so it's going to be this dihydrogen phosphate. And there's no other version of that. All right. Then we can use then the name to then write a formula. So I know here, this is my dihydrogen phosphate, which we just did up there. So I know that's going to be a PO4 with two H's. And there's a silver here. And I believe silver's ionic charge is just a 1 plus. So they neutralize each other and so on. I guess I should write that out, right? So Ag is a plus, H2PO4 is a 1 minus, or just a minus. Okay. And then these are already balanced, so then you get the formula of AgH2PO4. Okay. Same thing with this one. So the Roman numeral here tells us that it's going to be a plus. And bicarbonate, so CO3 is a 2 minus, but we have an H, so now that's going to be a 1 minus. And these are already in the right proportion, so then you have HgHCO3. And that's it.